Now we move on to the next type of classification of polymers, which is done on the basis of reaction path. So on the basis of reaction path of polymerization, we'll be seeing two categories. The first category we'll be discussing is the chain growth polymers. So chain growth polymers. Now, as the name suggests, they are forming chains, and we'll be taking an example. So let us just take a general example. If we have CH2 double bond CH attached with a group G, on polymerization, we learned that the process of converting monomer species into polymer was called polymerization. So on polymerization of this particular species or this monomer, we get CH2, CH, bonds will be open on both the sides, and there'll be G. And we have N units of this particular polymer. So now this reaction, this particular reaction, this polymerization can be done in three ways or taking three intermediates. So the first way that we'll be dealing with is free radicals. So free radical polymerization. So we'll be dealing with the free radical. Here in this free radical mechanism that we'll be observing that the intermediate formed will be a free radical. So we take initiators that are required to start the reaction, and the initiators here in this free radical mechanism will be, so this is a type of mechanism which we are dealing with, and free radical mechanism we have initiators which are somewhat like this, or we can have another one which has a structure like this, C double bond O, then we have the pH again. Now these, the name of these, the first one is called tertiary, so we'll be writing tert, then it will be butyl and peroxide. The second initiator which we have drawn is called benzoyl, and it is again a peroxide. So these two are the initiators that we'll be using for free radical mechanism. Okay, so these two, as we can clearly see, both of them are peroxide. So peroxide groups are the radical initiators. Now, how are they initiating the reaction? So let us just see the mechanism. Now, the first one, the first step which occurs is, suppose we are taking a general peroxide. Now, peroxide looks something like this. There is O group present, which are singly bonded to each other. Now, this peroxide, what happens is that it will break down to give us two radicals. So it is breaking down from here and we get 2RO, and since it is a radical, we put a dot on it. Now this will be referred to as IN dot, which is IN here stands for initiator. Okay, so initiator will be using this in the reaction. So now let us proceed to the reaction and see how we'll be using this initiator. So we have this initiator that we got because of this peroxide, and now we take our monomer that was CH2CH with a G. That is a group, any group you place over here. Now what happens is when we move on, this initiator will get itself attached, and how so? To CH2 of the monomer, and we have CHG. Now the radical is shifted on to this. So now this step is known as initiation step. As you can see, the initiator has attacked the monomer over here, and we call this step as the initiation step. Next, what happens is that this particular species that we just obtained, now this will be attacking another monomer. So we have got the same monomer because it was a chain growth polymer. So we are forming a chain over here. So when this attacks this particular monomer again, what we get is initiator then the CH2 group, followed by the CH with the G, that is the group, followed by CH2, followed by CH with a G. Now the radical is shifted over here. So we can see that it shifted from this particular CH and now it is on this particular CH. So this chain is growing as we can see, and therefore it is a reaction mechanism for the chain growth polymer. Now what happens is the species which we just obtained will now be reacting again with our monomer. So we have got CH2 double bond CH with a group. Now this will be attacking this and we'll again get the chain. So we'll get a chain, and this step that we are performing where we are making this chain grow, this is known as propagation, or call it the chain propagation. So in this chain propagating step, we are actually repeating the sequence with new and bigger radicals to carry the reaction forward. Okay, so there is this propagation which is occurring. Now next what happens is that we have to, now in the fourth step, now that we have got ourselves, so we have made the chain grow, propagate itself such that it now looks something like this. So we have a group here attached. So we have n units of this and the rest of it CH2, we have CH, this is the radical. Now this will combine with, so it will combine with another chain which looks like this, and it is having a radical over on it, and we have this particular group over here. So in this, that is the terminating step, what is happening is that we are reacting this with, suppose we have the chain again over here, so we have this attached to the same group. Say we have CH2 with an N over here and an IN, that was the initiator. So now what happens is that we have to stop this chain, that is we have to terminate this chain, and to terminate this chain we add both of these, and that will be the end of this process. So at the end we are left with CH2 with a CH and the group, and we have N times repetition of this, and we'll get our polymer. So this was the polymer that we are looking out for, and since both of these chains have combined, now both of these chains have combined, so we get this polymer over here. Now the initiator which we took was in small quantity, okay, and the intermediate which we, if we look at the intermediate in this particular reaction, it was the radical. So this radical here we can see that over here the radical being the intermediate is connected to this G group over here. Now this G group will be directly affecting the stability of this radical. And how so? So suppose we have, now we're taking monomer example. So if we have CH2 with a double bond and CH, and suppose we have the group as CH3. In the second example, we have CH2 again, and we have CH with CN as the group. So now if we notice both of them, the CH3 group is actually electron donating, and this C triple bond N is electron withdrawing. Since we have got a radical over here, the electron donating species will increase the stability of the radical and therefore will stabilize it further. So we can just say that electron donating species, or the groups, the electron donating groups, stabilize the radical. So they will be stabilizing the radical, due to which if we take the monomer, the reaction will proceed. If we take this particular monomer, and will not proceed if we take this one. So the reaction won't go from this, but it will be if we take this particular monomer species. Now, what if I take a third example, and here the monomer that we are taking is CH2 double bond CH with a phenyl group. Now this is called styrene, and here now benzene over here which is attached is an electron rich group and will donate electrons, making the radical stable, and so the reaction can proceed if the monomer is styrene. Now this is called styrene. Okay, so this was the free radical mechanism. Now moving on to the second type of mechanism that we can observe, which is known as the anionic polymerization. Now, the anionic polymerization is another mechanism that we'll see after free radical mechanism. And in this anionic polymerization, the initiators that we are taking is BULI, that is butyl lithium, or NaNH2, and these two are anions, or you can call them nucleophiles. So we have to proceed with this reaction where CH2 double bond CH with a group G will yield the polymer, which is CH2 CHG, and there will be n units of this. So we have taken n units of the monomer. So we have to proceed with our initiator such that this reaction is completed. Now let us begin. So we have got ourselves, now both of them are can be categorized as nucleophiles, and we know nucleophiles are electron rich species. So nucleophiles, now this nucleophile will attack our monomer over here, which is CH2 double bond CH with a G group, where what happens is this nucleophile would get itself attached, and we have CH2 with CH and the group. Now this CH over here will have the negative charge that was the lone pair of electron which the nucleophile initially had. In the second step that we'll be observing, what happens is that we have got this previous nucleophile attached to our monomer CH2 with CH negative and G group. So now this again attacks the monomer CH2 double bond CH and the group, leading to the formation of our, so since the chain is growing, therefore this comes under chain growth polymerization. And here we can see that we have the group, and this now the negative charge or the lone pair will shift to the last C. Okay, so this intermediate, as we can already see, the intermediate over here is with a negative charge, so the intermediate is nothing but a carbon ion, that is carbon with a negative charge. Now if we see that the chain growth, that is the propagation step, is occurring, so we have to stop this step to end the process and to get our polymer. So what we do is, to stop this polymerization, we have to put acid in it. Now in the third step we'll be putting acid in it, and we have the nucleophile attached to CH2 CH with a group G. We have n units of this, and now we have CH2 with a CH, that was the end one, and now this is the G group. So we put an acid on it into it, and when we put acid, so H plus is the acid over here, what happens is that the termination of the chain will occur, and the terminated chain will look something like this. So we have CH2, and now the negative charge is removed, and what follows is CH2 with a G group. So this chain is terminated. Now we already know that the intermediate was a carbon ion. So, and the G group, because it is attached to the carbon ion, will be affecting it directly. So, we'll be taking a few examples to see which monomers will give a feasible reaction. So, imagine the group being a CN group. And the second example that we are going to see is when this group is actually a CH3 group. So if we compare both of them, we can see that the Cn is actually electron withdrawing and CH3 is electron donating. Now, since we have a carbon ion, that is a negatively charged carbon over here, electron withdrawing group will favor this. So electron withdrawing group will favor this type of mechanism. Favors, okay, and therefore this will be used as a monomer, whereas this cannot be used. The third example which we took, and we'll be taking the same as we took it in free radical mechanism, is again CH2 double bond CH and a phenyl PH, that is a benzene ring attached. Now here we know that if there is a negative charge on this carbon with a pH attached, it can be involved in resonance and therefore it will be stabilized due to resonance. So whether it is through a radical mechanism or through an anion mechanism, will give both of them will be feasible when we have a monomer which looks something like this, that is the phenyl ring styrene, and styrene therefore can act as a monomer for both radical mechanism as well as the anionic mechanism. Now, if we see, now these are the two categories which we saw under our chain growth polymerization.